Good morning, good afternoon, and good evening, everyone from wherever you are. I'm Odysse Halim, and first of all, I would like to say thank you to the TAUP 2021 organizer that gives me the opportunity for a talk in this parallel session. And here I would like to present our recent work on the search of higher multipole radiation in gravitational wave from compact binary coalescences by a minimally modeled pipeline. This work is a collaboration work among authors listed in this slide, basically. And here is the layout of the presentation. I will show you the motivations behind this work, and then the higher multipoles of gravitational waves discussion. And the third will be the method of residual energy. And I will show the result of GW190814 and GW190412 reanalysis. And I will conclude everything in the end. So based on these two events, we have mass ratio which are quite asymmetric. For GW190412 is 0.3 and GW190814 is 0.1. And in fact, asymmetric systems are predicted to emit gravitational waves with higher mode. What does it mean, higher mode in this case? As we know that gravitational waves is quadruple, meaning that 2-2 mode. Meanwhile, with this asymmetric systems, we expect to have a higher mode than quadruple, such as 3-3 mode. And in fact, it has been shown from these two events, from these two papers, basically, that there is strong evidence of higher mode. In this case, GW190412, we show here time frequency map. The main signal is, of course, in quadruple. Meanwhile, if we put the track of 3-3 mode here is the dashed line that is not so clearly visible. But if we see the moment here, we can see that the alpha equal to 1.5 corresponding to 3-3 mode is basically quite significant. And moreover, for the GW190814, here, in fact, when alpha is equal to 1.5, the p-value for this higher mode is basically very, very low, which is something of the order of 10 to minus 3. And of course, the dominant mode is always present here, the quadruple moment. So higher modes can also be detected and reconstructed by minimally modeled coherent wave burst pipeline. And here CWB works on time frequency representation via WDM transform, Wilson-Daubesius measure. And this is to find coherent excess power, basically. This higher mode search is determined by optimizing the ROC curve. And this method, in fact, has been applied for GW190814 paper. And moreover, this method can be used to compare CWB reconstruction with the estimates from Bayesian inference. And here we are trying to detect the 3-3 multipole of GW190814, and it has been this method has been tested also for GW190412. This is quite fast analysis of higher mode, and this can support the model-based Bayesian parameter estimates. So the higher modes for gravitational wave multiples, especially for the frequency part, basically can be written in this relation related to quadruple main moment, which is the F22. And if we expect the 3-3 mode for the frequency will be related to m/2 multiplied by this quadruple frequency. And we define alpha is equal to m/2. That's why when alpha is 1.5, the quadruple, the higher mode is basically 3-3. And here we use similar two similar waveform models, which is COBNR for ROM and COBNR for HM-ROM. One is without higher mode and the other is with higher mode. And here the two waveforms are basically the same, except one can be turned on and off the higher mode. And here is the competition of on-source and off-source data, in which on-source is data period containing a signal, meanwhile off-source data is data period that is expected to contain purely noise. And then the CWB reconstructions is done with model waveforms with and without higher mode. And we calculate the residual energy in this case, and I will explain you in detail in the next slide what does it mean? And significance is estimated by comparing residual energy distribution in on-source versus the off-source distribution with and without higher mode. We also tune the delta alpha resolution in order not too narrow or not too wide. So the residual energy can be written in this equation, which means basically the sum of all the detector and the sum of each pixel that is that we are taking into account, and then the square difference of the WDM transform of CWB reconstruction for pixel I minus the WDM transform of a waveform model for pixel I. And in on-source, we use the sample waveform with maximum likelihood under Bayesian inference without higher mode. And then we calculate the residual energy. The idea is that if the CWB reconstruction has higher mode, if we calculate the residual against the non-higher mode, we will have the residual energy to be somewhat high, relatively high comparing to the other offline, the other off-source window. And in the off-source data, we do the Monte Carlo of 2000 injections, and we inject the higher mode and non-higher mode random samples from posterior distribution obtained by Bayesian inference. And we calculate the residual energy against only the non-HM, which gives us the estimated background distribution with minimal assumption, which means noise is expected to be stationary. Here is the diagram of the analysis in which one loop is for the null empirical distribution, meaning that we take a random parameter sample from the distribution, and then we compute the waveform without higher mode, and then we inject in CWB. We reconstruct, and then from this reconstruction, we calculate the residual energy back to the without higher mode waveform, and then we have the null distribution, of course. And then we do this for 2000 times, basically. And moreover, similarly for the other part here is that we take the random parameter sample, and then we compute the waveform for HM on versus HM off. In this case, we analyze until to get the reconstruction of CWB with HM. And then we calculate the residual energy without HM. And then we collect the output, which is the alternative empirical distribution in this case. And here is the result of GW190814. Here we show the residual in terms of time frequency analysis projected into the LIGO Livingstone detector. And we put the track of the 3-3 mode, which is the black dot line here. And then the red vertical line is basically the merger time, and meanwhile the blue vertical lines are the limit for the T-merger minus 0.5 second and T-merger minus 0.03 second. That is the data that we are analyzing. And then we put the slice of 3-3 mode here in this case on the right figure. And the result is that after doing the Monte Carlo simulation, we plot the histogram without higher mode, meaning that we inject without higher mode, and then we calculate the residual without higher mode. And then we have the purple curve, purple histogram. Meanwhile, we put the alternative hypothesis also in this plot, which is injecting on higher mode, and then do the residual without higher mode, and then we get the residual distribution. And the vertical red line is basically the on-source value. And in fact, this vertical, the on-source value is somewhat outlier comparing to the without higher mode with the p-value of the order of 0.0068. Meanwhile, this on-source value is somewhat consistent with higher mode with the p-value of 0.17. And moreover, here is the ROC curve of the analysis in which for several different alpha values, and we can see that for alpha equal to 1.5, the false alarm probability is somewhat low comparing to the alpha different values. And then here is the plot in another place of p-value versus alpha. And in this case, we see the dominant multipole is basically only 1.5, alpha equal to 1.5, which is corresponding to 3-3 mode. Here also we notice that there is slight fluctuation here, but this slight fluctuation is very small, given p-value very high, which means that the waveform of COBNR with higher mode is consistent with COBNR without higher mode. And then we analyzed also GW190412. Similarly, we put the residual time frequency map, and then we slice it to 3-3 mode, just to give you some idea. And then we calculate also the ROC curve, and we see that the alpha is when alpha is equal to 1.5, false alarm probability is the lowest. However, it is still quite high comparing to other modes. And then in fact, when we plot p-value as a function of alpha, we see that the when alpha equal to 1.5, the p-value is the lowest, but not so low comparing to other modes, basically, in which p-value is 0.03 for alpha 1.5, and besides there is also p-value, there is also alpha 0.5 with p-value 0.08 that may hint to one mode. However, based on these p-values, we cannot conclude anything, basically. And that's it. Here is the conclusion that can be drawn from this work, which is the method described here is extension of previous work. The method is complementary with other work, but we use full detector network and no assumption of noise Gaussianity, also difference in the construction and numerical treatment. And we applied the method in the discovery paper of GW190814, and this is the more detail of the analysis. And then we tried also GW190412, but the evidence is weaker for higher mode. And this is to notice that the consistency test between the reconstructed waveform by CWB and parametric estimates by Bayesian inference. And the final result can be described in frequentist p-value. A paper is in preparation anyway in this LIGO document. And here are references and acknowledgement, and that's it. Thank you very much. And if you have some questions or comments, please join the discussion panel on gravitational wave 2 on 1st September 2021 at 5 p.m. CET. And yeah, thank you.